The Large Hadron Collider, LHC, is one of the wonders of the modern world. It's believed to be the largest and most complex machine mankind has ever created. Buried deep inside the Earth, straddling both Switzerland and France, lies this massive structure where CERN scientists carry out experiments with huge implications for our planet and the rest of the universe. Some claims suggest that CERN destroyed the universe during recent experiments, resulting in us living in a nearby parallel universe instead. However, scientists recently stumbled upon something so shocking about the universe that the underground complex is at risk of being shut down. Scientists at the CERN Nuclear Research Center in Switzerland have succeeded today in producing record-breaking high-energy particle collisions. What has just been discovered in the Large Hadron Collider? Why is it shocking, and what does it mean for your future? Stay tuned as we bring you Switzerland's terrifying new discovery at CERN before they shut it down because it changed everything. There is something in Europe so large that it spans 2 countries. Despite how powerful this thing is, many people work and live right above it without knowing it is right under their feet. This is the Large Hadron Collider, or LHC, the zenith of human innovation. The LHC is not an everyday item, so it is understandable that many people live their whole lives without knowing about it. However, this invention is a time machine that will help us to find the actual meaning of the universe. This massive piece of human ingenuity is 17 miles in circumference and buried deep into the Earth at 175 meters. This ring-shaped object is situated under both France and Switzerland, another symbol of the power of collaboration in seeking knowledge. The LHC was constructed by the European Organization for Nuclear Research, CERN, at the whopping cost of $4.75 billion. The structure has gulped even more money for upgrades and maintenance. Why does the LHC exist? What is this monstrosity used for? As mentioned earlier, the LHC is our gateway to understanding the universe. The LHC works by speeding up 2 high-energy particle beams in opposing directions inside vacuum-sealed tubes that are supercooled. When these particles collide, massive detectors installed at 4 major points in the ring-like structure capture and record the outcome of these mini Big Bangs. The Big Bang might sound familiar from the wildly successful TV show The Big Bang Theory. The Big Bang Theory is the most accepted theory of how the universe came to be. The theory states that the universe started from a singularity before going through rapid expansion about 13.8 billion years ago. This very incident led to the formation of all the cosmic structures that you see today. By accelerating and smashing 2 particles at high speeds, scientists can recreate the conditions of the universe, or what became the universe, a fraction of a second after the Big Bang. This gives them insights into the fundamental forces and particles that constitute everything in existence around us. In this way, you can say the LHC is our massive microscope into the particles of the early universe, or a time machine that takes us billions of years back. The major component of the LHC is the powerful magnets, which need to be cooled to -271.3 degrees Celsius. Collisions have led to the discoveries of particles that have made scientists dizzy with excitement. They have helped to confirm theories that existed for decades but had no functional or replicable method of verification. One of the stellar works done by the LHC is challenging the Standard Model. But you may ask, what is the Standard Model and why should you care about it? The Standard Model is the most comprehensible theory yet that explains the universe's fundamental particles and forces without talking about gravity. It is like an instruction manual for the universe. It explains how particles like quarks, leptons, and bosons, which are the building blocks of protons and neutrons, interact with one another by means of strong, weak, and electromagnetic forces. The quarks are in 6 categories with different electric charges and masses. The leptons are made up of electrons, muons, and tau particles. These particles don't experience strong nuclear force and are important in making up the atom. The last are the bosons, which consist of photons that mediate electromagnetic interactions, W and Z bosons, which account for weak nuclear forces like beta decay, gluons, which bind quarks together with strong nuclear force, and the Higgs boson. However, despite the ability to predict many outcomes of physics experiments, this model has some holes and questions that it cannot answer. This is where the LHC comes in. The LHC continues to produce results that baffle scientists from its particle collisions. However, many of the outcomes are exciting beyond what you may think. An exciting example is the quarks, or more specifically the beauty quark. Scientists found out that when they decay, it is not according to the rules set by the Standard Model. From predictions, when beauty quarks decay, they should become muons and electrons at similar rates. However, the LHCb experiment generated different observations from what was expected. This hinted to researchers that there could be hitherto unknown particles or forces influencing these processes. This anomaly goes counter to the Standard Model and teases the existence of mysterious particles. This is not even the end. The big deal here is that the smashing of particles in the LHC sometimes produces strange particles that the Standard Model cannot explain. One example is the pentaquark, which generated a lot of attention in the scientific community when it was discovered. What is so special about the pentaquark? This particle represents a totally different arrangement of quarks. Unlike the way protons and neutrons in the atoms in the human body are composed of 3 quarks, the pentaquark contains 5 quarks. It includes what is called a charm quark, a charm antiquark, an up quark, a down quark, and a strange quark. The implication of this discovery was a whole new method of matter classification. This is because there could be other quark combinations waiting to be discovered. It also hints that there might exist a mysterious subatomic force that scientists have yet to understand. This is like finding a new rule that has been guiding us without our knowledge. Also, the statistical deviation of the pentaquark discovery was an astonishing 15, proving the high level of precision and power of the LHC. 5 is the standard deviation required to establish the observation of a particle in the field of particle physics, so 15 practically means it was no fluke. Equally intriguing was the discovery of the tetraquark, again by the LHC. This exotic particle is a 4-quark hadron named TCC+, which added a new chapter to the Standard Model. The TCC+ is a quartet of quarks containing 2 charm quarks and 2 lighter quarks. These 4 are held together by the strong nuclear force just like the pentaquark. The discovery of the TCC+ suggests that more quark combinations are possible. Apart from these, TCC+ can help scientists unravel the mysteries of quantum chromodynamics, or QCD. This is the theory of the strong interaction. QCD is a crucial part of the Standard Model. It is also the most complex component of particle physics. However, it is extremely rewarding to study QCD because it can explain how quarks behave under extreme conditions. The tetraquark discovery was mainly due to the LHCb detector. Researchers spotted the TCC+ signature while combing the debris of proton collisions, and it was challenging because TCC+ exists very briefly before decaying into other types of particles. The LHC has discovered that what is called the Higgs boson particle is heavier than earlier thought. What is the Higgs boson? It is a fundamental particle linked to the Higgs field. It was proposed by Peter Higgs in the 1960s. The confirmation of the Higgs boson particle itself was a grand achievement credited to the LHC. It is sometimes described as the particle that gives mass to other particles. The Standard Model actually predicts and offers a description of the Higgs boson, but it would take the LHC to confirm it really exists. The confirmation was thanks to the LHC's detectors, including ATLAS and the Compact Muon Solenoid, CMS. These allow researchers to study the debris resulting from particle collisions inside the LHC. ATLAS measures a particle's energy, momentum, and charge when collisions occur. Back in 2012, ATLAS reported it had found an unknown particle that fits the description of the Higgs boson. The mass was measured to be about 125 GeV per c squared. The CMS also confirmed this Higgs-like particle, but it could not measure the mass precisely enough to positively identify it as the Standard Model Higgs. Not long ago, after the LHC had completed more experiments and collected more data, scientists went back to studying the Higgs boson in more detail. It was then that they realized the Higgs boson might actually be heavier than earlier assumed. By analyzing the collision data collected by the LHC, scientists discovered evidence that this particle is heavier. That is, its mass is more than 125 GeV per c squared. The big deal here was the measured mass, which has caused some controversies. If the Higgs actually turns out to have more mass than theoretically predicted, it would mean we have to revise our understanding of the basic building blocks that make up the universe. This disparity is another area of physics entirely and could involve particles and forces that are beyond what the standard model can handle. The anomalies of the beauty quarks can also mean there are yet unknown particles or forces acting on them. Does this mean we are due for a replacement of the standard model? In addition, the heavier Higgs boson has prompted another critical look at the Higgs field and its role in the universe. Another fascinating theory that the LHC has contributed greatly to is the theory of extra dimensions, a theory that could help us literally see beyond the 3D confines of our universe. What is the theory of extra dimensions about and why are scientists excited about it? Consider these scenarios. Can you imagine this universe, as vast as it is, being just the tip of the iceberg? Imagine there are more dimensions than we are used to. This is what the theory of extra dimensions says. We grew up using length, height, and width dimensions to describe everything apart from the dimension of time. What if there are extra dimensions to the universe? What would these extra dimensions look like? Scientists say they could be compressed or curled up into scales so tiny that our current technologies cannot detect them. It is like observing a tightrope from a distance. It will appear one-dimensional to the observer. However, as the observer moves closer to the rope, they will see the rope's thickness and circumference. So, these extra dimensions may abound around us, but without us detecting them. Why are other dimensions important anyway if we have been getting by with 3? Well, scientists are trying to unify the forces of nature. Remember we said the standard model accounts for 3 of the 4 fundamental forces of nature. The recalcitrant force is the force of gravity, which has resisted every attempt to fit it into the standard model. Compared to the 3 forces of electromagnetism, strong nuclear force, and weak nuclear force, the force of gravity is very weak. This fact has confounded scientists for centuries. Introducing extra dimensions can neatly fix the problem, as this theory proposes that gravity is weak because it disperses into the extra dimensions. The LHC is crucial to this theory with its ability to delve into the subatomic sphere with accuracy. You have already heard that the LHC brings out anomalies like unexpected particle collisions and the quirky characters of some quarks. This suggests we might have things in the universe that the standard model is unable to explain but might be remedied by the extra dimensions theory. If we consider the Higgs boson particle that turned out to be heavier than initially assumed, the particle might be interacting with unknown particles or fields originating from these extra dimensions, which could have been responsible for the mass discrepancy observed in the Higgs boson particle. In the same vein, the mysterious rapid decay of beauty quarks could be the result of forces or particles influencing from the world of these unknown dimensions. Another interesting thing about the extra dimensions theory is that it can help us understand dark matter better. Dark matter does not produce, absorb, or reflect light. In fact, it was only detected from the effect it has on matter that we can see. Another reason that scientists are excited about the theory of extra dimensions is that it offers the tantalizing possibility of surfacing entirely new particles. It can also lead to discovering the forces active within the new particles. This is where the LHC comes in again. The massive invention can help to indirectly discover these potentially new particles and forces by analyzing lost energy and momentum during particle collisions. Of course, a direct consequence of this is the validation of the theory itself. If you have heard about string theory, it is another reason to be excited about the theory of extra dimensions. How so? According to string theory, the fundamental particles are tiny vibrating strings and not point-like dots. One thing is that these strings can exist in multiple dimensions. In fact, their vibration in 10 dimensions is required for producing the particles and forces that we see. So basically, for string theory to be valid, then extra dimensions have to exist. How do scientists use the LHC to detect the presence of extra dimensions? One major requirement is the ability to track the behavior of particles at very high energies. If you smash particles together at these levels of energy, what happens is the particles break down into their fundamental parts, exposing the fundamental forces and how they interact. As such, the interaction and decay patterns of these particles are very crucial in the quest for extra dimensions. Let's say we have successfully collided particles and we have got for ourselves a nice shower of subatomic particles. If we remain restricted to the dimensions we know, the energy and momentum resulting from this collision will only be accounted for in the particles that are familiar to us. However, if extra dimensions truly exist, it is possible that this energy and momentum could leak into them. This is what scientists try to watch out for, as the missing energy and momentum would expose these extra dimensions. Of course, these experiments are highly sensitive, and scientists need to find detectors that are sophisticated enough to detect even the tiniest discrepancy. Another approach scientists can use to pin down extra dimensions is decay patterns. When some particles decay, they break down into other particles in ways that researchers can predict, some of them governed by the Standard Model. However, these patterns can deviate from the Standard Model predictions if they are being influenced by unknown extra dimensions. So, what scientists do is to meticulously study the decay patterns of these particles and watch out for deviations. There is another interesting concept that can help scientists observe extra dimensions and even the role of gravity. This is called micro-black holes. Micro-black holes do not exist for real, but they can be hypothetically produced during high-energy particle collisions like what happens in the LHC. Some researchers have postulated that micro-black holes are more likely to be produced in a universe with extra dimensions. Why so? This is because even though gravity is a weak force, it may be stronger in these extra dimensions. So, if we detect black holes during particle collisions, it should prove that extra dimensions exist. Another fascinating and mysterious phenomenon in physics is quantum entanglement. This theory has more far-reaching effects than you can imagine in your daily life. It is like blending the lines between science fiction and real life. The concept of quantum entanglement is that one particle becomes so deeply connected to another particle that the state of the first particle influences the state of the second one. The influence is instantaneous, regardless of the distance between the two particles. The popular scientist Albert Einstein once called this concept spooky action at a distance. This theory, which challenges the very essence of spacetime, is an assault on our understanding of classical physics. When instantaneous connection or influence occurs between two particles, no matter their distance apart, it suggests that information is being exchanged between the two particles at a speed greater than the speed of light. This should not be possible according to Einstein's theory of relativity, which says nothing can travel above the speed of light. However, as confusing as it might sound, this is not what is happening with quantum entanglement, meaning it does not violate the law of relativity. CERN has taken a deep interest in quantum entanglement. The organization hopes to discover new ways to understand the universe. CERN wants to test the very limit of quantum mechanics and also study the area where quantum mechanics and general relativity merge. Their scientists have been performing experiments involving entangled particles through particle collisions and studying how the particles influence one another from different distances. The ability of the LHC to produce very accurate results lets the researchers measure the properties of entangled particles. If we gain a good understanding of quantum entanglement, it could open up new ways of comprehending the universe. For example, if particles can become entangled over large distances, can such entanglement occur across time? Being able to answer this question can improve our understanding of the linearity of time flow. In addition, studying quantum entanglement can lead scientists to new dimensions. This is because some properties of entangled particles suggest there are dimensions that we are unaware of. If we discover that entanglement occurs across these dimensions, we can gain insights into the structures of the dimensions and the way we can interact with them. Mind you, quantum entanglement extends beyond theoretical physics. It can usher in groundbreaking technological advancements as well. Take quantum computing, for example, where quantum entanglement is the basis of quantum computing. Here, entangled quantum particles can perform complex calculations that classical computers cannot even dream of. This can help in the fields of cryptography, drug discovery, and fields that require high and rapid computational power. You can even have secure communication channels that theoretically can never be compromised. CERN can also use quantum entanglement to finally unravel the mysteries of black holes and wormholes. With practical applications, it might sound like a wild dream, but wormholes can theoretically generate shortcuts through spacetime. You can literally step into a wormhole that deposits you close to a distant star, like an Uber for the universe. We might also be close to confirming the existence of parallel universes. Another dazzling concept being investigated at the LHC is supersymmetry, or SUSY. This theory tries to extend the Standard Model to generate a framework that ties together all the fundamental forces of nature. According to this theory, each particle in the universe possesses what is called a supersymmetric partner. This refers to a twin with similar properties but different in fundamental ways or behaviors. The basis of SUSY is symmetry, which physicists have used to account for the beauty and order permeating the universe's seeming chaos. SUSY proposes that every boson has a corresponding fermion and vice versa. This theory implies that the quarks and leptons existing around us have corresponding squarks and sleptons. The only thing is that these superpartners are yet to be discovered. Scientists take SUSY seriously because it can potentially explain dark matter, which we cannot see or interact with despite making up about 27% of the universe. SUSY particles are highly likely to be the building blocks of dark matter due to their stability, large mass, and weak interaction with ordinary matter. These exactly match the characteristics that astrophysicists suggest dark matter will have. How does the LHC come in the study of SUSY? It is the same collision process. Scientists can use the LHC to simulate the condition of the universe close to the Big Bang, and this will allow them to study the fundamental laws of nature. If SUSY particles actually exist, they could be produced and detected under these conditions. SUSY also gives researchers the necessary framework for understanding extra dimensions. In the same vein, string theory includes SUSY, and for mathematical consistency, it needs the existence of extra spatial dimensions. So basically, SUSY helps to stabilize the size and shape of these extra dimensions. It also proposes methods that their effects could be observed, like modifying the strengths of forces or the masses of particles as seen at the LHC.